Hello again, everyone. This is Mr. Reeves with you once again as we continue our exciting journey through solving systems of linear equations. And today we're going to be doing some problem solving with systems of linear equations, and we're going to solve those problems using the elimination method. All right, so here we go. I am looking at example 3 on page 256 of your textbook if you're interested in following along. It says the Simon family attended a concert and visited an art museum. Concert tickets were $24.75 for adults. Children paid $16, and the total cost was $138.25. Museum tickets were only $8.25 for adults and $4.50 for children, and the total cost there was $42.75. How many adults and how many children are in the Simon family? So if you watched any of my actually there were two previous problem solving videos with linear systems, one where we solved by graphing and the other one where we solved by substitution. You know that when we are solving a problem using a system, the first thing we have to do is identify our unknown. So we need to know what it is that we don't know. What are we trying to find? And the place to find out what it is you're trying to find is usually at the end of the problem. So right here it says how many adults and how many children are in the Simon family. And you'll notice that there are two unknowns, which is a great thing because a system of linear equations, at least for us, involves two unknowns. So I'm going to come over here and I'm going to let A equal the number of adults. And of course, we're talking the number of adults in the Simon family. And I'm going to let C equal the number of children. Okay, so we have our two unknowns. And then, of course, we want to create two equations, right? Because a system of linear equations, the ones we're doing, is two equations with two unknowns. All right, and so these type of problems are pretty nice, I have to say, out of all of them, because they kind of just lay it out for you. So concert tickets were $24.75 for adults. So for every adult that went to the concert, they paid $24.75, right? Let's see if I can make that a little bit neater here. 24.75, and that's for every adult. Now, if there was one adult, we'd go 24.75 times one. If there were two, 24.75 times two. We don't know how many adults, so I'm putting A, right? A is the number of adults, 24.75. All right. At that same concert, it was $16 for children. So I'm going to put 16. The same idea. If there was one child, it would be $16. Two children would be 16 times 2. Three children, 16 times 3, but we don't know how many children. So we put 16C. And we know that this is a total of $138.25. All right, that is for the concert. Then right below that, they tell us for the museum, it's going to be very similar. The museum is $8.25 for adults. It is $4.50 for children. And the total cost there is $42.75. All right, so the question then is, how many adults and how many children are there? And that is A and that is C. Those are our unknowns that we have in a system of linear equations. And we've learned three different ways to solve linear systems. We have learned that we can use graphing. We could graph these two lines. These are in standard form, by the way, and see where they intersect. And that point AC would be that ordered pair, AC would be our solution. We could use substitution. We could solve one of these equations for one of the variables and substitute it in. I definitely don't recommend that method for this problem. Or we can use elimination, which is the method we're going to use because that is the method we're studying. And you remember with elimination, our goal is to make two of these terms either the same and subtract, or my recommendation to make them the opposite and then to add, because when you add opposites, you get 0. So as I was looking here, took a quick look. If this were 4, that would be nice because 4 would go into 16 evenly, right? But 4 does not go into, I'm sorry, 4.5 does not go into 16 evenly. Now we could find something that they both go into, um, but looking over here, I noticed that this was 825 and this was 2475, and I happen to know that 8 times 3 is 24 and 25 times 3 is 75, so that got me kind of happy because I realized that if I multiply this bottom equation by 3, I can make those two the same. And if I multiply this bottom equation by -3, then I'll make it the opposite. So that's what I'm going to go ahead and do. I'm going to take this bottom equation and I'm going to multiply everything by -3. Okay, and once again, I did not open my calculator before I started the video. You would think I would get this down one of these days. All right, so here we go. So the first thing, I don't need a calculator for this one because I already knew that was going to happen. So I'm going to have -2475, right? That's what -3 is. And then I'm going to go minus, all right, and I don't really need a calculator for this one, but I'll do it for you guys. 4.5, that didn't sound very nice, did it? All right, 450 times -3 gives me -1350. And that's for children. Oops, what did I forget on here? I forgot the A, right? So -2475A minus 1350C. And then I'm going to do 4275 times -3. And I get -128.25. So I took that bottom equation and I multiplied it by -3. All right, I'm going to go ahead and rewrite that top equation right below it. 2475A plus 16C equals 138.25. And when I add those two together, what's going to happen? Next, let me go ahead and put a line right here. All right, these two, because they are opposites, will cancel. I have eliminated successfully the A variable. All right, what am I going to get right here? So 16 minus 13 would be 3, right? But 16 minus 1350, that's going to be 2.5. C. All right, and take a look at these. This was that 238 or 138? That was 1, right? Because this is 40 times 3 would be 120. Yeah. Okay, so the difference between these is just going to be 10, right? 38 minus 28 is 10, so that one's going to be 10 or $10. All right, and I happen to know that 250 plus 250 makes 5, and 5 plus 5 makes 10. So if I do this problem right here, if I do 10 divided by 250, I end up getting C is equal to 4. So what did I just find out? How many adults and how many children are in the Simon family? I just found out that there are 4 children in the Simon family. What do I still not know? I still don't know how many adults there are, right? All right, so when you have half of your answer, do you remember what you do? To go back to find the other half, you go to one of your equations. I recommend going to one of your original equations, although you're certainly welcome to use the equation that you created as well, because it will have the same solution, shared solution with the other ones. All right, so let's just go ahead and go to this top equation here. So I have 2475 times the number of adults plus 16 times the number of children. But what do I now know? I now know that C is equal to 4, right? So right here, instead of this C, I put 4 equals 138.25. So now I'm going to solve this equation for A. Well, 16 times 4 is 64. Okay, and then what am I going to do? Then I'm going to go ahead and subtract 64 from both sides. All right, so I'm going to go back to my calculator here, and I'm going to do 138.25 minus 64. And when I do that, I get 74.25. So 24.75 equals 24.75. A, that's important, right? We're finding the number of adults, equals, what was it, 74.25? And I'm sure hoping that this goes in evenly, right? If it doesn't, we would get part of an adult, and we don't want adult parts. Right, never mind. I'm not going to go any further with that comment. All right, I happen to know that 25 goes into 75 3 times. So I'm thinking it's going to be 3, but here we go. I'm going to do 74.25 divided by 24.75. And when I do that, I get 3, just as predicted. All right, so what did we just find out? We just found out that this family has 4 children and 3 adults. All right, so what do good math students and good math teachers do when they get an answer? If at all possible, they check their answer, right? So we use this top equation to get the answer. So I'm going to use this bottom equation to check the answer. So I'm going to say, okay, remember at the museum, it was $8.25 per adult, and I am now saying how many adults are there? There's 3. And remember that same museum was $4.50 per child. And how many children are we saying that there are? We're saying that there are 4 children. And what was the total cost supposed to be? $42.75. Let's see what our handy dandy calculator tells us. $42.75. That proves that this answer is correct because we found the one and only solution that makes both equations true. All right. Okay, so that is one type of problem solving that you can do with a linear system. This has always been one of my favorite, even when I was your guys' age, your age, because to me, the way the problem reads and the way the equations are written, it pretty much looks the same. There are some that are much more challenging, in my opinion, to set up. All right, so let's go ahead and take a look at another problem here. All right, and this is one of those problems I think that is a little bit harder to set up. All right, so this, as you can see, is on the bottom of page 257, your turn number 10. Contestants in the run and bike-a-thon run for a specified length of time, then bike for a specified length of time. Jason ran at an average speed of 5.2 miles an hour and biked at an average speed of 20.6 miles an hour, going a total of 14.2 miles. Seth ran at an average speed of 10.4 miles an hour, biked at 18.4 miles an hour, and he went a total of 17 miles. For how long do the contestants run, and for how long do they bike? So remember, when you want to know what you want to know, look usually at the end of the problem. All right, now after reading this, I realize it's really not too much different than the problem we just did. There is a relationship that you do need to know, and I've mentioned this before, and I most likely will mention it again. It is the relationship that says distance is equal to rate times time. Okay, this comes up a lot in math and in science. How far you go depends on 2 things. Your rate or your speed, which is how fast you're going, times what? The time. The faster you go, the further you go. The longer you go, the further you go, right? Distance is equal to rate times time. All right, so how long do they run and how long do they bike? Those are both what? Those are both times, right? How long is a time? How long is a time? All right, so I'm going to again assign two variables here. All right, I think I'm going to come down here and do it. So I'm going to let R equal the time running, right? And I'm going to let B equal the time biking. All right, that's a B. Okay, so here we go. So there are our two variables. Remember, we always have to start with our two unknowns. And now that we have our two unknowns, then what are we ready to do? Now we're ready to write a system of linear equations. All right, and we're going to use this idea that the rate times the time equals the distance, right? So here we go. Jason ran at an average speed. Remember, speed is another word for rate, or maybe I should say rate is another word for speed because we use speed a lot more than we do for rate. So we go 5.2, right? And that's running. So 5.2 times R. His rate times his time, all right? Plus, he biked what? At 20.6 miles an hour. That rate times that time is going to give us what? His total distance, 14.2 miles. So his rate running times how long he ran, plus his rate biking times how long he biked, gives us his total distance. All right, and that was for Jason. And if we read Seth's information and we just do the same thing, right below it, 10.4. Oh, how convenient is that? All right, and here we have what, 18.4, giving us a total of 17 miles. So we identified our variables or our unknowns, which usually they tell us at the end of the problem. We wrote our two systems of linear equations based upon this relationship here, and now we're ready to solve. And you heard me mention earlier, how convenient is that? Maybe you saw it as well. 10.4 is just twice of 5.2, right? So if I take this top equation and I multiply it by positive 2, those would be the same. But if I multiply it by negative 2, they will be the opposite, right? So I'm going to get negative 10.4R. So I'm again taking this top equation and I'm multiplying everything by negative 2, right? Minus, all right, 20.6 doubled, all right, is not 40.12. It's 41.2b. And again, if we weren't sure, we could go ahead and use our calculator. 20.6 times negative 2 gives us negative 41.2, right? All right, and then negative 2 times 14.2 is going to give us negative 28.4, right? Okay, and then what do we have? Then we have this system right here, which we then can add together. Why are we adding? Because we created a pair of opposites, yeah? And when we do that, what happens? These cancel, and we get 41.2 negative plus 18.4. Let's go ahead and use our calculator there. Now, the 41.2 negative is already in my calculator, so then I'm going to go ahead and add the 18.4 positive, and I'm putting these two together, and when I do that, I get negative 22.8. Negative 22.8b. All right, and then over here, I've got negative 28.4, and I'm going to add that to a positive 17, and when I do that, I get a negative 11.4, right? And now I'm ready. Now be careful, this one is bigger. I'm dividing a smaller number by a bigger number, actually. It's a smaller number because it's negative. But if we consider the absolute value, right? Okay. A negative divided by a negative is a what? It's a positive. Many times students would say the answer is 2 because 22.8 is half, right? It's half of 11.4. I'm sorry, 22.8 is twice of 11.4. So 11.4 is half. So the answer is 1/2. Okay, and you could put this in your calculator and you would see. So what did B stand for? B was the time biking. So the time biking is 1/2 of an hour, or if you prefer, 30 minutes, right? But we were doing this in hours because it was miles per hour. All right, and then what do we still have to find? We still don't know the time running. All right, so to find R, we would plug it back into one of these equations. But you know what? I'm going to leave that for you because the point of this video is to solve the problems, to set them up and solve them. And we've done previous videos on actually doing the finding the solution part here. So we set it up, we found B, and then you would go back and find R. All right, so I'm going to let you do that on your own so that we can move on to another problem. Okay, all right. I think this one right here, we're just going to go ahead and set it up and not do any of the solving. So we've got Bryce, and I'm not going to read through every word here. He spent some money on apples, and he spent some money on pears. And he could have gone, he did that at one store, he could have gone to another store and spent more money on apples and more money on pears and had a total cost. So how many apples and how many pears did he buy? So again, we're going to go to the end of the problem. Before we write equations, what are we going to do? We're going to identify our variables, right? So A is going to be the number of apples bought, right? And this is by Bryce. And then what else do we have? Then we have pears. So P is going to be the number of pears bought, right? Okay, so here we go. Write equations to represent his expenditures at each store. So I'm going to go ahead and write it like I've been writing it, like this. All right, so here we go. So this is going to be just like what we've been doing, right? How much? 5.26 on apples at the first store, 64 cents. All right. Oh, wait. Ooh, I was not being careful. Mr. Reeves. Let's read carefully here. He spent 526 total. So that's going to be over here. That's his total. That would be a lot for apples. All right. The apples cost 64 cents each, right? And the pears cost 45 cents each. So there would be that. And then at the next store, all right, the apples worth only 32 cents each. Half the price. Again, that's very convenient, isn't it? All right, and the pears were 39 cents each. And at this store, because the prices were lower, he only spent 362, right? Okay, there would be our system. I hope you could see that if we took that bottom equation and if we multiplied it by -2, right? That would give us the opposites there. We could add those two together and continue solving from there. All right, so again, those have all been pretty much set up the same way. All right, let's take a look at this one here. At Raging River Sports, polyester-filled sleeping bags sell for $79. Down, excuse me, down-filled sleeping bags sell for 149. In 1 week, the store sold 14 sleeping bags for $1,456. All right. So here they're telling us what the variables are, and right here it says write a system of equations you can use to find the number of each type sold. All right, so the number of each type sold. So they told us, excuse me, so X is going to be the number of polyester filled. I'm just going to put poly filled. I hope that's okay with you guys, right? And Y is going to be the number of down filled. Okay, so what are we looking for? We're looking for two equations. All right, now this one is going to be a little bit different. It says at Raging River, polyester bags sell for $79 and down sell for $149. In 1 week, the store sold 14 sleeping bags for $1,456. All right, so this is going to be a little different because they didn't give us this many plus this many equals this total and this many plus this many equals this total. So the previous three problems we set up were all basically the same way. But what does it say right here? In 1 week, the store sold 14 sleeping bags. All right, so X is the number of polyester bags filled sold, right? Number, maybe I should write sold after here to make it clear. So what do we know? We don't know how many they sold of those, and we don't know how many they sold of those, but what do we know? We know they sold 14 total, don't we? Right? Does that make sense? Okay, so if you refer back to one of the previous videos when we were solving, I think it was with substitution, when I said we have two equations a lot of times. We have a number equation. Again, that's not hashtag. That's a number or an amount. And then we have a dollar equation. This is an example of that. So it could be 7 and 7, right? Could be 8 and 3, could be 13 and 1. All those combinations have to add up to 14. And then what else do we know? We know, and this is like the equations that we were just writing. It's $79 for one of these, and it is $149 because down is so much nicer than polyester. And that total, right, is, let me erase this and give us a little more space here. Actually, let me write that whole thing over. $79 for every polyester filled plus 149 for every down filled gives us a total cost of 1,456. Okay, so do you see how this second equation is just like the equations we were doing in the previous three problems, but this one is different. Instead of giving us two different equations that gave us a cost, they gave us one that told us the number and then one that told us the cost. All right, and then again, I'm not going to solve this, but this would be one. This actually would be a good one to use substitution on because you could get that x by itself or that y by itself. Or we could take this top equation, right? And we can multiply it by, whoops, that's not part of the equation, Mr. Reeves. We can multiply it by what, negative 79 if we wanted to? Would that be a good idea? And make those opposites, or negative 149 if you wanted to? Again, if I were solving this, I would use substitution. I would take that top equation and go x equals 14 minus y, or I would do y equals 14 minus x. But since this was the elimination section, that's what they wanted you to do. All right, so I hope you can see the difference in that type of problem where they give you the amount sold and then they give you the cost. You're gonna come across problems like that. All right, one more problem and then we're gonna be done in this video. All right, so twice a number plus a second number is 310. The difference between the two numbers is 55. Find the numbers by writing and solving a system of linear equations. So what does it say right here? It says find the numbers. So we have two numbers. All right, so I'm going to let x be the first number, and I'm going to let y be the second number, right? And I'm going to go ahead and write my system. I'm just going to use this space right here. All right, what do we know? Twice a number, so 2x, right? Because twice means 2x, plus twice a second number, 2y, is 310. So twice that first number plus twice that second number is 310. The difference, and you should know difference means to subtract. The difference between the numbers is 55, right? So this one is actually, if you know your math vocabulary, this one is not too bad to set up at all. And again, we could use whatever method. It didn't specify. It says actually explain how you solved. So we could graph these and see where they intersected, right? We could use substitution by solving one for x and one for y. Or we can use elimination, right? We could take maybe this bottom equation and multiply it by 2. Yeah, and if I multiply that bottom equation by 2, what would I get? I would get 2x minus 2y equals 110. And why did I multiply it by 2? Because that top equation is 2x plus 2y equals 310. And I hope you can see this is coming together very nicely, right? Because what's going to happen with these two? They're going to cancel. Those are going to be 200 apart, and you can solve it from there. All right, so when we are solving a system of linear equations, what do we do first? When we're solving, sorry, let me restate that. When we are problem solving using a system of linear equations, what do we do first? We find and identify the unknowns, right? We find and identify the unknowns. And where do we do that? Usually at the end of the problem, right? Then what do? Then we write a system of how many equations have we been using? 2 equations, right? And then what do? Finally, we solve the system, and then we check our solution, okay? Now that solving the system can be done by graphing, it can be done by substitution, or it can be done by elimination. Because ultimately math is about solving problems. All these skills that you learn, the goal is the same, to be able to use the skills to solve a problem. Just like a calculator is a tool to help us to solve problems, elimination, substitution, and graphing are tools to help us solve linear systems. All right, I hope this video helped you in your understanding, and I hope you have a great day. Thanks, everybody. Bye.